experiment because.
Yep. Yeah. This depends on a monotonic thing happening. So if your data look like the top right, the Spearman is not right, the Pearson is not right. I don't know about parabolic correlations. It's a really good question. I just don't know. The problem with that is you have to have an inference about where the inflection point is in order to fit something. You might want to do something like curve fitting. So another thing you can do is, again, what's so beautiful about this method, I know I sound like I'm in love with the method. I think I literally am in love with the method. But the thing that's so beautiful about it is if you want to try a different metric completely unrelated to these, you're welcome to. So for example, what came to my mind was I would do curve fitting. I would say, I suspect there's a parabolic data here. I use MATLAB, I don't use R. I would do curve fitting. I would say, okay, fit the best parabola to this data. And you'd get some parameters, right? Here's the AX squared plus BX plus C. You'd get an ABC, whatever your slope is, whatever thing you care about. Maybe it's just how it, and then I would just scramble my data 10,000 times. And each time I would run the curve fitting tool and see how extreme of a fit I got. Again, right, it's the same principle. What I literally saw when I did it with my data was this, and I had a certain slope. When I scramble my points 10,000 times, little various fits will come up like this and this and this and this, and you'll know if it's significantly different. Otherwise, you have to use like a chi-squared goodness of fit test or something. But chi-squared has its own problems. It's a continuous distribution that assumes discretized inputs, which doesn't fit. Doesn't matter. I just wanted to crap on it. So all these assumptions. So this is great. So whatever you're doing, whatever method you're doing, you can apply the same idea, which is what's your real statistic? Now just scramble the data and try and do a statistic 10,000 times and see how it could happen. Just the same exact data, just noise. I do it with machine learning. Here's how good my my ROC curve is. And then when I scramble all the labels a bunch of times, I do, these ROC curves and you see if it's better. Did that answer? Cool. Yeah, I like that. I've done that a couple of times where you just curve fit. I suspect this is it. Could it have happened by random chance? Did I just get lucky? Anything else? Great questions. Really enjoying them. I feel like you guys are getting it. It does take a couple of days, right? For all the for me to say it, I had 10,000 times in order for it to bake in. Okay. Greater than 2 categories. Here's your visual animals part. So I have group 1 and group 2, and I made some measurement on them. And here are the resulting data points that I got in each of these groups. Would you say the means are the same? Yeah, means look pretty similar, right? They are the same. I made sure they're the same. Now, which group do you feel like you're more confident in? If you had to report the means for these, no statistics, just use your intuition. Are you more confident that you have the correct mean for group 1? Or are you more confident that you have the correct mean for group 2? Group 2, right? Why? Perfect. Bingo. Very concise. There's a lot of spread. All your numbers end up there. You can just sort of intuit that that's a pretty reliable phenomenon, and this is a less reliable phenomenon on the left. And so I guess I would just call this generally, I should have put this on here, signal to noise. Like, okay, here's my signal. And in this case, the signal or the measurement's the same, but the noise is higher in group 1 than in group 2. And so we intuitively know it's a less reliable thing. And if we bootstrap this data, we'd get a mean that's all over the place. And if we bootstrapped group 2 data, the mean would be much more tight. So our confidence intervals would then reflect our intuition for what certainty should be. Another way to think about that, so we're sort of like abstracting all the things we just did about signal to noise, is there's something called the F statistic. And what the F statistic is, it's by knowing what group something belongs to, how much can I explain about the data? So for here, for example, I'm box plotting. Box plots are great. UCLA, USC, and Irvine's data, and the boxes are the interquartile range, the middle 50% of the distribution. And if you didn't know anything about what school someone went to, your best guess for the salary would be the red dotted line. If you had no information, right? I just observed 210 salaries, 70 times 3. If I said, hey, what's the mean? You'd say, well, it's the red dotted line. And then if I say, hey, now I have information about these groups called UCLA, USC, and Irvine, It's just one factor, but it divides into these three groups. If you look at the data, now you're able to make a better prediction, right? If I said, okay, what's the most likely salary of someone given that they go to UCLA? Now your best guess is the dark line on the left. And if I said Irvine, it's the dark line on the right box. So because I gave you information that was useful, you're now able to make a better guess on what the mean might be. Do we sort of follow that intuitively, that when you have no information, like you just literally, if I were to ignore the labels, red dotted line. But now that I have information, I'd say, well, UCLA makes less than the average, the global average. So that's there. And if it's Irvine, they make higher. So my best guess is there. So another way to think about science and our discoveries is that every factor piece that you discover it's a little bit more information that lets you make a better prediction. So if I know that you're a vapor, I will have a higher prediction that you're going to get lung cancer. Like, that's the information. If I know you use anabolic steroids, you have a higher risk of heart disease, et cetera, et cetera. If I know you have this variant for Parkinson's, you're more likely to develop Parkinson's disease. I don't totally know, like there's still some noise given that I know it, but usually I know better. And that's kind of the big point, but that's what you're doing. You're adding pieces of information in the world that when somebody knows them, you're now able to parcel out two different groups. Same, I don't know, what kind of research do you do? Glaucoma. Yeah. What's a factor that causes or is related to glaucoma? Yeah, and okay, great. So if I were to say, what's the global, risk for glaucoma, you'd give me some rate. Yeah. And if I then said, oh, well, here I actually measured the intraocular pressure for every individual. Now for this guy who has a high intraocular pressure, is his likelihood up or down? Up. That's what we're doing in science. We're taking whatever we have here. If there's two different groups and you think about them like this, here's a risk for getting glaucoma based on high intraocular pressure or low intraocular pressure. You now have some ability to make a better guess. So you're discovering factors or features or information that leads to a change in outcomes. And the way we might quantify that here is that by knowing what that factor is, intraocular pressure, I now am able to explain a little bit more of the noise out there. It's no longer just a guess about whether you get glaucoma or not. I now can say, well, if the whole range was here, I now know that, well, these people are here and these people are here given that measurement. So the factor is allowing you to explain the different likelihoods of getting glaucoma.
And what about all of the other variables?
Perfect. And what about all the other variables? So maybe a physicist or a statistician would say, well, if you gave me all of them, I could tell you every single one. If you found all the relationships. Isn't that how we do it in science? Why do people get cancer? I don't know. Why do people have seizures? Well, they used to think you were witches and they would burn you at the stake because there's no discriminatory power there. And then we find out, well, there's something going on with your brain. Okay, that's cool. Oh, this thing called, now there's a division, epileptic seizures and non-epileptic seizures. Okay, with epileptic seizures, now we can find out that they're generated in different foci with EEGs. Okay, then and then what kind? Is it general mall seizures? Like down, right? So it's just this tree of knowledge that you're finding out. And every time you tell me another piece, I can do a better job at diagnosing what's going to happen. What's your risk factors for getting cancer? Okay, well, right, it is whatever it is. And then, oh, you have BRCA1 mutation? Okay, now it's this. Now, are you homozygous or heterozygous? Now it's a little bit, and you refine. And the more factors you know, the more you can explain. Imagine that you start with being able to explain nothing. We're just guessing what the average is. And every time you tell me something meaningful, I can explain a little bit more and put it into buckets and say your risk, you don't have a BRCA1 mutation, your risk is no longer 5% or whatever it is. It's now 0 to 1%, and that all that range shrinks. So you're explaining the spread in the data. That was a long diatribe, I know, but I feel like that's probably what you should walk away with. Is that if you were to measure everybody's intraocular pressure, you'd have no idea how anything relates to that. And as you measure it, you can reduce those numbers, that uncertainty. What's another test you do besides intraocular pressure that's related to glaucoma? Yeah, great. So then you come in and you do visual field tests. Now you're even more sure. And at some point you become so sure you make a diagnosis. Or you put them in your study, whatever it is that you do. So that's the top part. That's the signal. this factor lets me tell these two groups apart in terms of what's going to happen to them along some variable. Now, the bottom part is the noise. It's everything left over. It's when you look at this, just because I told you it was UCLA, sure, you can make a better prediction than if you knew nothing about the school, but some people still make a ton and other people make less. If I then told you what their employee position level was, you could probably eliminate more of that noise, right? Oh, you're faculty and you're part-time or whatever. You can start to, but there's still going to be a little bit of noise. Well, you got an R01 grant and you didn't get an R01 grant, so you got a salary boost. So in statistics, that's what we think about it. The top is, how does what I'm testing, my little groups, how does my group explain what's happening, divided by what about everything that's left over? Everything I can't explain. And that's how we think about it here. There's some effect, but even though I know you're in group 1 or group 2, I'm less certain about group 1 because there's all this noise I can't explain. I can explain a little bit more of group 2. So it's this ratio, signal to noise, and an F statistic, we'd call it explained variance divided by unexplained variance. Here's how the features you told me explain what's going on, and here's what's left over. And another way you might see it is sort of between the group variability, which is, okay, well, here's the 3 groups you told me. That gives me this much differentiating factor between them. I know the difference between USC and UCLA is whatever amount it is. That I can explain now. That's between the groups. And then the noise is the within group variability, which is at UCLA, there's still a whole bunch of spread I cannot account for. There's nothing in my model that accounts for all the spread in those salaries until I add faculty position. So signal is between the groups. I can now tell this apart, and noise is what's left over. And if you just think about that as signal to noise ratio, then you'll run across the F statistic a lot. This is what pops up in ANOVAs. This is what pops up in ratios of standard deviations to compare spread between groups. This is what happens when you add new factors into models to say, hey, did this new factor meaningfully contribute relative to my old model? Blah, 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 blah. It's all this. It's all the F statistic. It's the same thing every time. Do your factors matter in explaining divided by what's left over that they didn't explain? And if you can explain a lot, high F statistic will likely be significant. And if you have a ton of noise, you're going to have a low F statistic, and it's not going to be significant. All right, so any questions on the F statistic? And it applies to 3 groups or 2 groups. T and F tests are the same with 2 groups. It's the same thing. It's all looking at the same stuff. How different are my groups and how much noise is there? So let's open up the ANOVA example in R. Any questions online? Love my silent group. All right, here's the ANOVA example. Oh my God, I've been teaching this so long. Okay. Oh my God, it's like, hey, it's been 3 years. Nice. You guys are my 3rd anniversary class. Great to be here. So we're going to use a different data set mostly because I'm lazy. I didn't ever recode it, but there's this built-in plant growth data set. So this is built into R. R has some built-in data sets that you can just fiddle with. I didn't use this before, but I wanted to introduce you to it. This is the assignment variable. It means the value in plant, whatever plant growth is, I'm going to assign it to this variable df for data frame. And whenever I play with variable df, it's the plant data. This is like equals is a bad operator. This is what's really going on when you code. Whatever's on the right-hand side is getting attributed to whatever the variable is on the left. This is a much more intuitive way to think about it, but it requires 2 keystrokes, so no one uses it. Okay. It's funny in life, right? Great. So I have a little function here that I created. It's called fstat, and it calculates the F statistic. So we don't have to go through all the monotony of that because that's not what this course is about. You could replace it with any statistic you want, but the F statistic has really nice characteristics that I just explained. It's like the median is for skewed things. It's the right metric most of the time for things like this, ANOVA included. It's just a good one. But like I said, what I taught you applies to anything. You can still pick a crappy statistic, but you will get an answer. So the F statistic just takes in, okay, here's my data frame. The plant, let's print this out so that you see it. Plant growth. So here's what it looks like. It's 20 or so, yeah, 30 entries. and it has a weight for these plants, and the plants are in either the control, they're in the control group, or they are in treatment 1 group, or they are in treatment 2 group, and there are 10 samples in each. So the idea is that you took a bunch of plants and you either did nothing or you gave them, let's say, 2 different kinds of hormones, and you saw, did they grow in weight at a different rate. So when you knit all this together, we're going to do exactly what we did before, which is we have, here's our permutation tests to obtain our p-value. So that's in the loop just as you normally see, and our p-value's here, and then I print it out. Just like we always do, what's the actual F statistic you have? With your actual data, I observe a ratio of signal to noise of whatever my F statistic is. I guess this is it. And then the permutation test, we do just like you did before. I pre-allocate my 10,000 buckets, so there's room in memory. And then each time in this for loop, each of the 10,000 times, I do the same thing, which is I shuffle all my data. So basically all the 30 plant weights are now going to be assigned to random groups. Because we're going to say, remember the permutation, there's no effect, so this data could have turned out many, many, many different ways by random chance. So I assign them to just random groups. So sometimes the plant with weight 5 that started as a control will now be in treatment 1 or treatment 2, and then we'll calculate the F statistic and see how messy the F statistic is just by chance. And then calculate it and just store it in this bucket, each of my 10,000 buckets, and then I print it out. And so here's what that looks like. So my F statistic most of the time is 0, because if you give me a bunch of scrambled data and I randomly divide it into 3 groups, what's the difference in means between those 3 groups on average? 0. Just like if I took my salary data, put it in a bucket and shuffled it and randomly pulled out 70 samples of each, my most likely difference is 0. But sometimes there's a difference just due to random chance. All the high numbers ended up in one bucket and all the low numbers in another one, and the average numbers in the third one, and there's a big difference in means. The between group variability, the signal, was high. So you get an F statistic. What you'll see is that with the usual color scheme, green is what we actually saw. It's 0.36, which is right here. And you can see that chance doesn't get a value that high very often. It doesn't happen. So our p-value is correspondingly low, 0.01. So there is a significant difference here. Now my question for you is, what did I just show? How would you put, remember in statistics we're working on when we have to, being really rigorous about what exactly we said. So I didn't tell you the answer yet, but if you've ever played with ANOVAs, what did I just show? What's the effect? Cool, I have a result. What does that mean? What's different from what?
I think it's the need in one of the groups, whichever one it is that is significantly different than the other two.
Okay. How do we know which one?
I mean, I would probably.
You probably what?
I would just probably.
There you go. It's very close. That's a very good, thank you. Anyone want to refine that? You can do that. So that's sort of how we do. If you find a result here, I'll touch on that in just a sec. Has anyone used an ANOVA before? Is it a little scary that we don't know what that means? Like what it's actually testing? I honestly don't think I knew it until I taught the class. It's just I know that when you have multiple groups, you're doing ANOVA, and if p is less than 0.05, then you're good. But does anybody know what it's testing? Between what and what, or whatever, yeah. That's even closer, actually, yes. A difference in what? Yes. Great, so that's the answer. So an ANOVA is testing, are the means of all the groups that you put in exactly equal? So it's like what you said, but sort of from all perspectives. Like is anything different from anything?
the means equal?
My hypothesis in this case would be that the means of all the schools are not exactly equal. So my null hypothesis is that all the means are exactly equal to the global mean, which is that red dashed line, which is if you didn't know anything, basically it's saying the things you told me about school is completely irrelevant, and it's no different than if I was just going to guess the global mean. That's the null hypothesis. So say your hypothesis that you want to get an R1 for, reverse it, and then try and prove out how many ways the reverse could happen and compare the same formula over and over again. So that's what we did here. And then you're right that this is called an omnibus test, and you want to start with an omnibus test. It's a test which encapsulates multiple groups into one test. I just did one test to test if all of them were equal. Did you notice I didn't pairwise compare all of them? Once you've shown an omnibus result like this, you are allowed or accepted to go into all the pairwise comparisons and find out which ones are driving it. You might find out that none of them are driving it. You might find that one group's a little high and another group's a little low. And so when you compute the total, all the pairwise comparisons, when you compute pairwise comparisons, none of them are significant. But if you zoom out and looking at all together, there's something going on. Something is different from something. So you don't always, so you can get a significant ANOVA and not a significant follow-up t-test, pairwise test.
But you can add also the first test like a 130 after one-way ANOVA to test between, because one-way ANOVA will be between A, B, C, D, and then you want to see with the post test to see maybe they are not all different, but maybe A and B are different, and then B, C, D, they are the same, but then I have to difference between A and B.
Yep, so exactly. So he's making the point that you can do those pairwise comparisons afterwards. And some people will let you get away without doing correction for multiple comparisons because you already showed there's an effect, you're just sort of uncovering it. And other people would say you still have to correct. So we'll get into that in just a minute. But do we get the ANOVA, what we did here? Are all the means equal between all the groups? No, something's different at a P level of 0.01. You can do it with 4 groups. You can do it with 10 groups. But that's what ANOVA does. And now what's great about this is if you have a repeated measures ANOVA, then you would just stitch together the pieces of information that we already thought, which is instead of swapping all of them, you know, let's see if I look back at this plant data, if instead of it being 10 dependent plants, it might be that you started with 10 and then you let them grow and then you gave them treatment 1. So you have 2 measurements on them. In another group, you started and you let them grow, and then you gave them treatment 2. Then you have paired data, right? The same plant will have 2 of these measurements, and so you would link them. And when you shuffle, you just swap them for each linked pair, just like we did before. That might be a little technical, but what I'm trying to point out here is if you embrace that, you can, whatever your funky experimental design is, you can work with. And if you have subjects or animals that only had a couple samples and then dropped out, you don't have to throw away their data. You know, if you have repeated measures, how, you know, maybe you have 3 measurements on people, and sometimes we have students that sign up and do 2 of our brain exams, they don't do the 3rd one. Well, if you're relying on the traditional test, you got to axe that row because you don't have complete observations for them. But in a permutation test, you don't. You would just code it up and say, okay, well, swap their first and second brain data, but just ignore their 3rd brain data because there's no value there. Blah, 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 details. It's flexible. Okay. Any questions on ANOVAs? Did you notice it was the same technique we used before, we just had 3 groups instead of 2, and we used a different statistic. All right, we're not, okay, so, yeah, okay, great. So here's the summary of all the things that we learned. Here's the slide to look at if you want to use the functions in the future. If you have 1 group, let's start with 2 groups because it's simpler. So you have 2 groups, different subjects. The question you're asking, your hypothesis, is the mean different between these 2 groups? That's usually what you're asking. Now, for magnitude, you would bootstrap each of the samples, like we talked about, and if you wanted to say if it was really significantly different from 0, you would shuffle the group assignment across. That's the shuffling, that's the permutation test. So you run that. Now going back to 1 group, how come I don't have a hypothesis question for 1 group when I only have 1 group? every comparison you make has to be against something else. There is no statistical test with just one group. Is something different from what? So I won't go through them all, but these are the things we covered. Bivariate data, you're asking, are these variables meaningfully related? Is variable A related to variable B? Not is A greater than B if they're the same type of variable, but are they related at all? So these salaries from one university to another, sure they're bigger, but is each one related? So you bootstrap the subjects and you shuffle one condition across. It's all the details. I don't want to give you this. If you want to look back, then this is the summary of it all. There's too much to cover. So now I want to get to your point of multiple comparisons, which is, we'll start with the theoretical. I have a 20-sided die, and I have one roll on my 20-sided die. What are the odds that I roll the number 1? 1 out of 20? Yeah. What's that as a fraction? Either, yeah. 5%. 0.05. Oh, how convenient. Okay, now I roll the dice 30 million times. What are the odds that I roll the number 1 at least one time? Pretty darn high. Almost as close to a human could get to 100%. Really likely it's going to happen. So this is the multiple comparisons problem that we deal with in science, which is if you run one test, we're willing to accept that even if there was no effect, you would have had a positive result 5% of the time. That's the p-value cutoff, right? That's, of all the noise that you looked at, your test at somewhere, and there's a couple of times noise was even bigger than what you saw. But we're willing to accept that. 5% of the time. But if you run 10 tests, just by random chance, those false positives are going to stack up. And it is going to be likely that results that your paper overall is not true. And so you have to do a correction for it. So what I want to do is run through a confusion matrix for you, which is how we do predictions in science. Machine learning specifically, this happens a lot, but just in science, which is there is some truth. Gravity is real. Smoking causes cancer. Vaping causes lung cancer, whatever. There's some truth. And either it's true or it's not true. Drinking lots of water leads you to wear Donald Trump Halloween costumes. Like probably no relationship. So that'd be a negative. So it's positives and negatives. There's things that are really happening in reality and not happening. At least that's how we think about it. And then as scientists, we're not gods. We don't know the truth, but we do make predictions. So either, yeah, a positive one might be, yes, smoking does cause cancer. And another prediction might be, a negative one might be, vaping does not cause lung cancer. That could be a result of a study, right? So you're either validating it, you're either saying if there's something going on or there's not saying something going on. And behind the scenes, either there's something going on or there's not something going on. So there's just 4 ways things can turn out. And some of them are easy. That's like smoking causes cancer. Now we have the data, it shows it does, positive, hit, good. We like those. You discovered something real. Congratulations. There's a true negative, which is drinking a lot of water leads you to dress up like Donald Trump. Probably not true. And if you collected data, you could probably show that's not true. With me? So this is how the world could turn out. This is the world, and this is your predictions about the world. Now, there are other ways. So you can get things wrong. You can have a false negative, which is when there really is something going on that vaping causes lung cancer, but your data were either insufficient or you just got unlucky and they did not show a significant difference. So it's like a miss. You missed an effect that was really there. So same thing. You'd call a miss a false negative. Just easier to think about. So that's your type 2 error. When you think about errors, when you hear about it, type 2 is that one. That's the way there's only 2 errors because you can either get it right twice, 2 different ways, or you can get it wrong 2 different ways. So that's type 2. What is type 2 error related to when you write grants? What do you have to show when you propose a study? What'd you say? Power. Power. What do we usually hit for power? What's the power? You want to have a what percent? 80%. So 80% means that your type 2 error is only 20%. It means you are going to gather enough subjects that if there really is something true going on of the effect magnitude that prior literature has speculated is true, you don't miss it. And not even because you did a bad experiment, you might just not have enough data. That's just the statistics of it. That if the cancer rate's low, it's 1%, and you only collect 10 subjects, and you run your permutation test, you just might not have enough data to reject it. So power analysis is is 1 minus that. It's the opposite of that. You want to have 80% power, lots of subjects. Does that make sense that something could be true? I hope, like, if this was my plot and this is 0 and here's my effect, it's not exactly equal to 0, but if I only collect 4 points, that may or may not pass a significance test. There's just not enough points. There just happens to be enough noise where it's not totally clear. So that's why you do power analysis. Problem is you don't always know the effect magnitude beforehand. But grants want them, so that's what you do. So that's type 2 error. I think that's maybe easier to understand. And then the other one is a type 1 error, which is a false positive. Where does false positive and type 1 error show up in science?
When you're actually at 5% of the
Yes! Yes. Love that. Yes, that's the p-value. And that's the burden that we generally put on there of 0.05. Usually we call it alpha. This is type 1, alpha, type 2 is beta. So power is 1 minus beta. So yes, the false positive is exactly that. It's all the times when we look at our graph that I brought up over and over again, I should just copy and paste it. There's a lot of slides. That one. That's it. That's a false positive. Because if you're above 0.05, then you're going to reject the null hypothesis and say you found an effect. But we know, because we simulated it, that random chance could have produced that result some fraction of the time. So that would be a false positive. We would say there's an effect, and it's actually due to complete random chance. Sorry. But that's the type 1 error. And so there's a balance between type 1 errors and type 2 errors. Given that you have a certain number of subjects, you either have to go one way or the other. You have to either be more stringent, and you'll reduce this. But if you're more stringent, then you have to have an even stronger effect or gather more subjects, or you'll just have a bigger, you'll miss more. Here's an example. What if I made my p-value 0.01? That's the new criteria in science. You may only publish if your p-value is 0.01 or less. And you'll say, well, you'll definitely have less erroneous reports, but you'll also have people whose p-value comes out to 0.03 and it was a real effect, but you had to reject it. You couldn't publish the paper. So there's that trade-off. So there's always, it's literally just a trade-off. You can't get more of one without getting less of the other. Can't get less of one without getting more of the other, maybe clear. Get that? So there's this teeter-totter. You'd love to just hit everything on the diagonal, but you don't. So which way are you going to screw things up? All right. So it's written down, but I think that was clear. Incorrect rejection of the null hypothesis. Failing to detect something that was real. And again, not because you're a bad scientist, because you're underpowered. Which is funny. You're not underpowered. You just don't have enough subjects to reject a null hypothesis. And in retrospect, that might be underpowered. All right. Anything else about this? Oh, we did that. The one thing I want to talk about here that I didn't put on the slide. So this is I didn't tell you how to solve it. So most people would say there are just statistical corrections you need to make. And the most simple one, the intuitive one, that isn't right, but is intuitive, that was around for a while, was the Bonferroni correction. And that's the idea that if you run 2 tests, then you just are going to double your p-values. So they need to be twice as significant each. So if you ran 2 tests and one of them came out to be 0.03, the p-value now is 0.06, and it no longer passes the 0.05 threshold. Does that make sense? Run 2 tests, double the values. You have 3 tests, triple the values. So that's the problem. The more tests you run, you now have these penalties where your results better be pretty significant in order to pass the alpha type 1 error cutoff that we set. That turns out that was shown decades ago, but somehow not that many people have caught on to be overly strict. So the Bonferroni correction is certainly strong enough, but it's actually mathematically too strong. And again, it came out of an era when people did a bunch of calculus and theory. And what happened was this guy named Holm came up with the correction. I think it was in '78. That's an algorithm, like this stuff. It's not a distribution. It's not an assumption. You do this iterative thing, and it's called the Holm Bonferroni correction, and it's just a slight modification where you take your most significant p-value. If you did 4 tests, let's say, you take your most significant p-value and you multiply it by 4. Same thing as Bonferroni. Then you take your next most significant p-value and you multiply it by 3, next one by 2, and the last one you leave as it is. And that ends up being the actually accurate way of correcting for false discovery rate. So I would use that. There's functions for it. So your most significant result still has to be just as significant, but this iteratively rejective sequence, they call it, is the best way to do multiple comparisons correction and not overly penalize your results. You can if you want. So you write it down. Holm, Bonferroni. I really should put that in there. How do you spell Bon? Is that right? I'm the world's worst speller. Holm, Bonferroni. Is it? Oh, shit. Well, we'll just leave it. It needs to explode like a star. I was so amazed when I discovered this. I've been using it ever since, but I'm always blown away that people don't. Oh, that's not it. People don't use it. Close enough. Cool. Yep. Great. So use that. Talked about this. This came up randomly, but just someone asked me how to bin histogram data. You bin histogram data, in my view, until it becomes so fine that you get these discontinuities that are not representative of what you're actually caring about. So over here, you start to bin it so fine that you get these little gaps that are probably due to random chance, and that's not helpful to look at. This is probably the right level to look at. Totally random, but a little bit of visual ideas is good. All right. So now we're going to go over the rules. So, okay, so I always say Z. 0, your visual animals, like I say, always plot the data. No matter what, do bar plots, scatter plots before you start running stats tests, because honestly, it's happened to me so many times where I jump right into stats and I regret it. So look at your data, trust your brain. Nobody cares about your sample data set. There's very few exceptions. You care about the underlying population distribution. You sampled 70 people in each group, but you care about the millions that really comprise them. So you want something fundamentally true as a scientist. That's what you. Engineers care about just making things work. Scientists care about discovering the fundamental truth so that you can take shortcuts in the future. That makes sense? You're always caring about the truth. Unless you're doing like a fingerprint retinal scan to get in a door, then you care about matching the exact person, but almost nobody else cares. You care about just the truth. Bootstrap. So that's resampling with replacement. You're just taking that die and rolling it a whole bunch of times in order to quantify how uncertain you should be in your magnitude of your effect. So if your cancer rates, if the correlation between vaping and cancer is 0.5, bootstrapping is taking those data and rerunning your experiment so that you can put confidence intervals on that correlation. So that you could tell your reader, I'm actually only certain it's 0.1 to 0.8. I'm hugely uncertain. You permute for significance. So when you say, is this effect real? Is it significantly different from something? That's a permutation test, and that's the shuffling. And I put in the same language here because a shuffle really is no different than if we're to take everybody and put them in a group and draw them out one by one in random order, but without putting them back. Eventually you get everybody. You basically just shuffled. So sampling without replacement is just shuffling. So you're going to shuffle your data, and then you redraw your groups, and you see what differences could have happened by random chance. P-value is exactly this and nothing else. It is the probability that you will have observed the data that you saw, given that nothing was real. And fortunately, in the age of computers, you can just enforce this. That's been the take home. You can literally just scramble your data so that there really is no difference between your groups and see what would have happened. That's the magic. No assumptions, few assumptions. So said another way, it's what fraction of the time are your chance things that you build, all that shuffling, greater than what you actually saw. And another way to think about it is sort of how often, and this is like sort of in quotes, how often would you be wrong in discovering that there's an effect? So there's really no effect. So some fraction of the time we're willing to accept that you have a false positive, but there's really nothing there. The hard work is all the shuffling we did. It's super easy to calculate the mean or ratio between two groups. What's hard is to understand what could have happened due to random chance. So it's easy to see the salary difference between UCLA and USC, 16 grand. It's harder to know if that's unlikely or very likely because there's a lot of noise in the salaries. So that's, you do the permutation test. Shuffle them, take the difference, see how often that happens. And to build your distribution, you say your hypothesis, and then you break it by doing the opposite, by shuffling, and then calculate the statistic that you care about 10,000 times. So we just did that over and over and over and over again in various forms. Correlation, scramble the data. Paired data, shuffle the data. Two groups, shuffle the data. Curve fitting with a nonlinear effect, shuffle the data. And the confidence intervals on everything. Okay, that's the end. Yeah.
Where did the 10,000 come from?
That was inherited to me. Just what people recommend. It gives you 3 decimal places of significance, and that's as many as any human cares about. Sometimes I do 50K if I'm really feeling annoying about it. 10K is fine. Like, it's just, you know, when you first get into science, you're like, oh, every little thing matters. And at the end, you're like no one seriously gives a crap if it's 0.012 or 0.015. Nobody cares. And it's probably not real. There's probably so much noise in the exact sample that you got and all the biases you injected into your own data that that's the last thing to worry about. But it's, you can see it's super fast. If you want to make it 100,000, do it. Take you 10 seconds. It's just harder with machine learning stuff when you have, like, you know, 100 variables and you're doing a big XG boost decision tree. It's just ugly. It takes a long time. So sometimes I'll get away with 5,000 or 1,000. Because if it's really pretty significant, it'll show up. What else? Same as you would run any other statistical test on. If you feel comfortable running a t-test, you should certainly feel comfortable running something that has even fewer assumptions about distributions. I don't know, we all come from different fields. Like, I wouldn't run an MRI experiment and return a result with less than like 8 samples in each group. Less than 8, I would just do a Wilcoxon sign rank test, or do a permutation test, but get rid of the magnitude. It's just do 1, 1, 1, 0, 0, 0 for, like, that represents above the mean, above the mean, above the mean, below the mean, below the mean, below the mean. But you can do it with fewer if you're just trying to get a feel for it. I guess it really comes down to whatever your field is. Are your reviewers going to believe you? Like, I remember Jack Gallant, he was a famous neuroscientist, and he had this incredible paper where he would scan your brain while you watched videos, and then he would use your brain activity to reconstruct what you saw from your brain data. He would build images from YouTube. He would, like, use YouTube things, and he would average together thousands of videos to construct what you saw. Have you ever seen this? That's the paper. Where's the video? I'll pull it up. But and the idea, he only had 2 subjects because it was just so, it was it was science or nature, I can't remember. Where's this video? Here it is. How do I, this is the clip. So here's what he showed, and here's what he reconstructed. I mean, it's not perfect, but it's not terrible just from brain activity. It even has the banner on the bottom. Yeah, that's crazy. So look, it sure isn't perfect, but that was from scanning your, like, several of your visual networks at high fidelity. And he had 2 subjects, and that was a nature or science, I don't remember. What is it? Nature paper.
You wanted to kind of get deeper in the weeds and really understand this code line by line, like what's the next resource you utilize to understand the inner workings of the code that you
I spent a lot of time on it. I really hope if you were to sit down with it, it would be clear because I comment every single line what it does. And if you don't know what something, like there's only one maybe confusing line when you like flip rows, I would just Google that in R and it will tell you what the function does. Like I think it's flip if. Like I basically roll a bunch of quarters for all the rows for the paired data. And if it's a 1, I swap the pairs. I just shuffle them. And like I said, if you had 3 groups, if you had repeated measures ANOVA with 3 groups, you would just shuffle that entire row. Like all the same principles apply. So I would give it a shot. And if you don't get resolution, email me. But I hope somebody reads all the comments. I spent a lot of time putting them. Yeah. So the point about this, just to make sure it's super clear, is you need as much, you know, there was science before statistics. So if your data are really convincing, like I forget your name, but if you have really convincing plots about, you know, knockout mice versus regular or whatever, you don't need, I don't even know why you put statistic. It's so damn obvious. Or visual data, sometimes you're like, cool, that makes a difference. So we can talk about what to do with it, but 2 subjects is fine when you show me that. It was crazy. They had to put them in these MRI scanners, and they molded custom face plates so to their exact face, and they would put in the scanner so they couldn't even move a millimeter. And then they would scan them because you need every little piece of your brain to be totally lined up between sessions. They would sit there for hours and just watch video. So if you have a lot of data but few subjects, then that's probably fine. Yeah. They were going to give them full body casts. So you couldn't even move. You're like literally just stuck there. It's like totally terrifying. Yeah.
That's really like a machine learning. So they are giving them a lot of images, and then they will see the pattern, and then they will just train that machine learning, and then show that picture, then it will be the same pattern, or like for colors and shapes and all that.
That's a good start. It's more complicated than that. You have to have an encoding and a decoding model. They basically, you know, but the problem with that methodology is you don't want to construct clips from other clips they've seen. So what they actually did was they showed users a whole bunch of clips, but then they took a whole bunch of YouTube clips they've never seen before, and they ran them through how they thought the brain worked and how it extracts lines and features and shapes and different regions, and then said, okay, let's use that as a basis set with which to construct this one based on activity. So it was, yeah. This is 10 years ago. Probably a lot better now. Spooky, huh? From your brain. Yeah, we want to do it when people sleep. See your dreams. Yeah, cool. So, what other questions do we have about statistics? Yeah, I fell asleep in a scanner. I find it really comforting. It's like a big hug. What else? Yeah.
What about Twoway ANOVA?
Yeah.
When you have 2 groups, you have the knockout, and then you have the treatment. And then you do Twoway ANOVA, but then you don't find any significant result. But then if you are performing the monitoring test, then you see that you have a significant result between the knockout, but not between the treatment, or you have between the treatment, but not between the knockout. Then you will put in the legend like Twoway ANOVA not significant, or and monitoring test is the significance, or you could perform also like a t-test between the treatment or between the genotype.
Can you boil the question down again? Because there was, I think, a couple in there. So do you want to say, can this test be used with Twoway ANOVAs? Or do you want to say, with Twoway ANOVA results, what do you do with them?
My question is that if I can use t-test also when you have like 2 variables, it's correct.
You can certainly, yeah.
Say that it's not correct, but you should use Twoway ANOVA and then see.
I think we're maybe confusing a way with a factor. So there's 2 different dimensions to describe ANOVAs in 3, actually. But you might say you have your control group and your treatment group and your treatment group too. You get two different treatments. So what are you calling this? If this is my experimental design, what are you calling this setup? It's a one-way ANOVA, what with 3 factors? Yes. Okay, great. And here you might say, I don't know, let's call it male and female or something. Now it's a 2-way ANOVA, right? So okay, so now we got that. So what part are you asking? And we're clear. Sorry, sorry to ask you. But when you do this, what will happen when you put this into a traditional ANOVA software is you'll get a p-value or a statistic for this axis, and you'll get another p-value for this axis. And if you allow it, you'll get a p-value for the interaction, such that, yes, there's an effect, but only when females get treatment true, because that ties into the estrogen system in a way that the other ones doesn't. Right, so that's a possibility. It wouldn't be true on average if you just averaged across all the groups, but specifically with this treatment, there's something going on. Does that make sense? How you can have it, that's called an interaction effect. It's only true in one if, as the coalesced, the intersection of 2 different things. Okay, so now what?
Then after you perform a post-test, because you want to see
the
difference between the treatment 1 and treatment 2.
Yes.
But not taking into consideration male and females, only males.
Okay. Yeah, you can do that. Totally. If your ANOVA came out to be positive, I mean, that you rejected.
Sometimes, ANOVA it's like there's no difference, but then you have these little differences.
Yeah, that could be. What do you want me to tell you? I mean, if you ran 2 tests, then you should correct your values, because you're just p-hacking, and we all do it to whatever degree that we do it to, because we want a grant or whatever our reason is. It's hard to pre-specify all the things you want to test in an experiment because things pop up. So I'm just saying, if you test an ANOVA and get no result, and then you pairwise test these 2 groups, ignoring that, you did 2 tests. You may not report that you did the ANOVA, but you certainly did. And the reason that he's actually pointing to a good technical point, which is let me just diagrammatically explain that, I think, which is, let's just say that I didn't have my UCLA data. Let's say I only had, let's say I didn't have USC. I'm just gonna block it out. I only had Irvine and UCLA. You might find a significant difference there if you did a pairwise test. Yeah, we did it. That happens. Sometimes what happens though is if you add another group into your ANOVA, and let's say there's noise all over the place, what you end up doing is you add a lot of unexplained variability that we didn't even know existed before. I didn't even know salaries could get that high, let's say. And so you can actually have this could be significant by itself, but once you pass in a bunch of noise, your unexplained variance then blows up. So this number ends up getting big, and it makes your F statistic small. So if you add it, if one of your groups that you add in has way more noise than everything else, you're not gonna be significant, even though one of the pairwise comparisons is significant. Does that make sense? Because it's kind of like, oh yeah, God, UCLA and Irvine, that factor really explains the data well. And then you're like, oh my God, I didn't know all this noise existed in the general data. So that if you were to not have this group, you'd have all this noise now that could be unexplained variance, and you're only explaining a small fraction of it. And like, especially with USC, look, the mean of USC is basically the same as the global mean. It's not really adding too much information, and it's not adding any more than Irvine and UCLA by themselves. Your best guess for a salary at USC is just the global mean.
But it's compulsory to use the one-way ANOVA in this situation.
You say compulsory?
Yeah, so it's like,
yes.
bad if you are using the t-test between the groups.
Yes. Yes. If you have, I mean, I don't know. You're the experimentalist. If you feel like, oh, USC isn't really relevant, and then you just report that as a pairwise comparison, like, that's on you. It's your choice as an experimenter and what you're going to tell the paper.
Right. I feel like that last point was saying, like, how are you telling the story of how you're doing the data?
Sure. What are we talking about? Are we talking about what you should do or what people are actually going to do? Because no one will listen. right? I mean, I'm just saying, if you ran a test and it becomes non-significant to your story because it didn't turn out, you theoretically should report that you did that test and just not talk about it all in your story because you did it. That's the multiple comparisons. You did the comparison, you just didn't like the dice roll you got.
I have another question.
Yeah, later.
So if I have like a graph, if I have like a graph with multiple points like this, and then wait, this is then I should do one-way ANOVA.
It looks like you have
because then no, it's like the same points, but then I will do a t-test about the last point, and then I will have let's say time.
Okay. Well, that's not an ANOVA. ANOVA is for discretized groups. Right?
Okay, but
Group, non-ordinal data. You can't do an ANOVA on something that's continuous.
okay, so in this case, what I should do? Like a t-test from the last point?
What you're trying to say,
Or-
you're trying to show that the trajectories are different?
Yes.
Yeah, I
So
would
like-
show, I would fit it to the curve use of, in your brain, I think a lot of statistics is like, again, you have this intuition, you're just trying to unpack it into hardcore math form. We all like, okay, I get what he's saying, and now all we're trying to do is just convert it to math. Like, you get it. Okay, I totally get it. You want to show this trajectory. It sounds like if I was you, I would fit a log function to both of them, and I would fit the slope of that log. And, or if you, now it's linear, so fine. So now I would do a linear correlation between the two. And if these are pairwise points, I would subtract them first and show that it's greater than 0. Are they pairwise? Is this point linked with this point?
No, because
No.
two different
animals.
groups, yeah.
Yeah, so you do 2 correlations and you want to show that the slope is different. So every time, perfect, what a great example. I would use this data, I would use the permutation method, I would fit a correlation to one set of data and a correlation to the other set of data, and I would subtract them. And say if one had a better slope than the other, bigger, and then I would scramble the data and do it again. He has a custom statistic that he really wants. You want to show the slopes are different. Don't you want to show the slopes are different?
No.
Maybe you don't know. What do you want to show?
No, I want to show that, like in the end, there is an effect. It's not from the beginning.
You only
but
care
in
at the end. Well, then
No,
why even?
I care about could be also here at the beginning an effect, but I get this effect only in the end. But then I should test all the points. And the thing is like how I will.
I think you want to show the slopes are different still. All you care, right? Because if the slopes are different, they will have different trajectories and they will be different as you go through time.
Yeah.
But then you only have to do one test. See, this is it. If you go through and you do test, there's 5 tests. I don't want to do 5 tests and correct for them. So I would do one test. I would show that there's a positive correlation. There's a difference in the correlations that's greater for this one than it is for this one. And then I would take 10,000 times. I would just, each time you just scramble your points and run the correlation again. And you already have, it would take you 5 minutes to do it with this data, with this code. And what's that? And it would spit out a p-value. Yeah, but I get it. So you have time and you have some measurement and you want to show that they're different at any time, ideally.
Yeah, but it's only at the end.
But you mean what you're actually seeing as a result now is only at the end, but you're worried that any sane reviewer would say you should have tested, how did you cherry pick the end? So again, I would do an omnibus test. This is a perfect example, and I would fit the correlation to both. Correlation A, correlation B, B minus A. You were hoping for a positive number. Or you could, I think there's any other better way to do that. Can I ask you something? If and you guys, everyone feel free to leave, but I think it's kind of fun to walk through actual problems. So let's say that your data are this, and so everyone can see them, they look like this. Would a positive result be if they had the same slope, but they were just higher? Is this a result? Same exact slope, but they're different the whole way. Is that a result? So then you could again fit a regression line and take the intercept and show that the intercept, that there's a constant scalar offset between this group and this group. That's what you're trying to show. You don't care where it happens. You just want to say that accounting for time, there is a difference given group A versus group B at any time. So the problem is you don't want to do pairwise comparison. So let's collapse it into one single omnibus metric, which is either the intercept or the slope. And I would calculate the regression, take my slope, and then just do that with a permutation test 10,000 times. And sometimes my slope will end up here and here and here and here. And other times my slope up with this data will end up here and here and here and here and here and here. But overall, it's not ever going to be as big as it was with your real data, is my guess. And if you show me your data, I'll help you with it. Why are you asking me? Yeah, great. Who has a question with data they want to publish? It's okay.
I like that example. So can you talk about why subtracting the two? Is it because they're technically paired because it's the same time point?
Are they paired or not? Not paired. You could subtract them too. Another way to do it would be I would subtract them all, and that will give you, again, it's just you walk away with slightly different interpretations of what's happening here. So you could subtract them all, and that would map onto, here's my times, and here is my, I use a different color. Here's my difference between the time points across time. And here, I got one here, and it was no difference here, and here, and here. And then I would just take the mean and show that it's different from 0. I would take each of my animals across these times, and I would perform this and come up with one number for each animal, assuming you have many animals. And then I would have, then for each animal you have, what's the average difference between group A, exposure A and exposure B in this experiment? You're basically assuming that the effect is constant across time. That's what you have to assume there, right? Because if it's not constant across time, then you'll get some big differences here and small differences here, and that will add noise, and you will be less significant. Right? So it's always about picking the right metric for what you want to do. Does anyone understand that last point, that if he actually had if the slopes were different, he would have a big difference here between green and black and a small difference here between green and black. And when you did those subtractions, you actually then have more spread in the data. Same mean, but more spread in the data, and you don't want that. You want to minimize spread, but have the same signal effect size. So you can pick the metric that works and has the. Cool. You could do them as a fraction of the same point then too. It's just normalized to the first point being 100%, which it sounds like you already do. All right. What were you? Did I interrupt you, or was that your question? I don't remember.
No,
Cool. So again, looking at the data. So a lot of this is like, I'm kind of realizing this myself for the first time, that the whole point of this is it frees you up to use the proper metric for what you care about. That actually fit the data. So median in the case of distributions, and if I had my way, I would do correlation, and look at the difference. And that's a nice omnibus test, but I don't know what the statistic test would be to that difference correlation. So I don't know, maybe it's there.
I have a lot of questions.
Okay.
Okay. One is, like, in your examples of the correlations, there was one in which it kind of looked like a correlation, but there was an outlier.
There's an outlier.
Like, in that case, is it okay to take that out? Like, when is it okay? When is it not?
Well, I'll show you. I gave you the tools to analyze, and I forgot to tell you about it. So with RStudio, if I pull up my bootstrap, my one sample, here's a fun way to diagnose an outlier. Let's say I take my data. I got to remember what this data looks like. All right, so here's my data, and I'm going to plot it. So let me just take, what is this, 70. So I'm going to take one point, and I'm just going to make it an outlier. I'm going to give it a huge value. So my salaries, so let's see if I remember R. So salaries, 71 equals, I don't know what is, these are all, here's 10 million, let's do make it a million. Did you put a semicolon in R? No, do I need this? No? Thank you, bro. All right, so I just made this point an outlier. So now I'm gonna save this, and hopefully it doesn't propagate to the next class. And I'm gonna put it together, and we'll see what the effect of an outlier is on our data. Oh, I did median, I think, so there's no effect. I think that's why you use the median. So let's switch that back to mean. It totally matters on what your data look like. That's the take home by the skewed data.
That's subjects, or you have to tell why you are eliminating that subject.
Estimates of the test statistic is that. So what am I changing? Maybe I have to, am I doing US? Oh, I'm doing USC. Sorry guys, it's gonna take me a sec. Yeah, okay. Yeah, now it gets uglier. All right, so you'll see that when I now estimate what my statistic is or my variance, it used to have a nice clear distribution. Now it's messy and gross because it's been pulled up by my bootstrap, because some of the time I get this massive outlier, and that'll change my confidence intervals now. So now, okay, so let's just look at the value. So my confidence interval, my test statistics at 93, my confidence interval is this massive range because I added in an outlier. And if I just want to show you the clearest example. Let me show you a different one. So that's the correlation, salaries correlation. Yeah, probably clearest with the correlation. Go to my data, most of my samples. I'm doing UCLA, what am I doing here? USC Internet, okay. Let's see what happens. So I can do this on the fly. Yeah, okay, there you go, finally. All right, so here's what happens. So if I take my original data, then what we've looked at before was when I do the correlation between the salaries, I get a high value. I got the correlation, I think it's USC and UCLA, it was 0.77. So my correlation is in green, and my confidence intervals are in blue there. You see that? Okay, there were no outliers. Now let me add this outlier in, and we'll look at exactly the same plot. So I'm changing 1 point to be an outlier. Now I get a whole, what we call a bimodal distribution there, 2 clear discernible peaks. Why do I have 2 clear discernible peaks now when I only had 1 and I've only ever seen 1 before? What's up? This one's a correlation.
Is it like that part is all the time that you take the highlight, the outside?
Yeah, exactly. That's the outlier, which is when you introduce an outlier, when you do your permutation test, if it happens to get shuffled into, if the million happens to get matched with a high salary, then the correlation looks great. Looks super good. Oh, you make 150 grand at one school, you make $1 million at another. That's still a high correlation. And if it gets shuffled to one of the other random spots, then it gets a really low correlation because it looks flat. Everything's going up except for this 1 point that's all the way out here. And so what you get when you have outliers is you get bimodal distributions, and any good statistic that you care about should converge to something with central tendency, meaning a mean or a median. How much faith would you have in something if it's like, well, half the time it's this value and half the time it's this completely different value? That's not reliable. So if you've noticed, and you probably haven't noticed until we drew this by contrast, whenever you do these bootstraps or these permutation tests, you should get a pretty, doesn't have to be a normal distribution, but you should get something that has a clear, obvious chunk of where the statistic lives, or it's a bad statistic. So in this case, it's not the bad statistic, it's that I have an outlier. And sometimes the bootstrap, sometimes the shuffle matches up with a high point and I get a high correlation. Sometimes it matches up and makes my line look terrible. It's basically like, you know. So whenever I shuffle whenever I do a bootstrap and this isn't here, I get a nice fit. And whenever I happen to get this point, it looks pretty flat. And that's why I get that second curve on the left. So a good way to diagnose outliers. And if you have a less extreme outlier, it'll go down. That's not an outlier anymore. But did you get the point that outliers can be diagnosed now by looking at, if your data don't have a nice central tendency, you should look at what, I haven't done it yet, but I would gladly use that as a reason to exclude something. Or use forced standard deviations or whatever your thing is. But again, the problem with standard deviations is it's based on a normal distribution. So what's nice about this is it's based on its effect on the outcome statistic, making it unstable and unreliable. Seems like a very good reason. This 1 point completely makes a bimodal distribution when it was very clear before. Yes?
So how do you How do you know whether or not you should take it out and whether or not you're?
I would take that out. If you saw that plot, would you take it out?
Well, what if there's multiple points there? Should you follow them out?
Everyone always asks the outlier question because no one has a clear, there's no formula for it. So whatever you can justify. That's not a formula, but what is it, 3 standard deviations or 4? 3, I think. Like 3 or 4 standard deviations is the usual rule, but again, that's based on a standard deviation being meaningful. And at least in machine learning, did everyone take roll? Come on, y'all. So in machine learning, especially when you use like a deep neural net or something with high interactivity, like it's really difficult to tell what should and shouldn't belong. So again, I think the only way you can assess those things is by what it does to your results. Not like what? Who has bimodal? Yeah. You can have bimodal data, but usually you're not calculating a bimodal outcome.
You're saying that if you bootstrap
Mhm.
and generate that distribution.
Yeah, and you have 2 humps, cut.
One-to-one inflection
Yeah.
point.
Yep.
Something's off.
Yep. Exactly that. It's super.
Normalize it a little because it
Exactly.
totally makes sense, but like, how would you?
God, that's the tough part, right? Everyone's like trying to fall back on, you know, some formula that somebody arbitrarily made up as 3 standard deviations. It's just another tool. If you think that makes sense and it fits your data and your viewers would accept it, then I would use that. I think it's more convincing. Because yeah, a lot of the stuff lately I've been doing is machine learning, and just because something's an outlier in in an input doesn't mean it's an outlier in how it affects the output. That's the transformation. The problem with outlier detection is it focuses on the input and not on the output. When what you care about is the output. You care about your effect, that you're, you know, does it change my prediction of the correlation between vaping and cancer? Not, is his age 3 standard deviations outside of anybody else's? Because maybe that doesn't matter. It only matters if it affects the outcome, if you ask me. But I can understand both points. So I always get this question. I never have a good answer because there isn't one. What else? Sure.
I don't know if you guys talked about this maybe yesterday. Did you talk about the ratio?
Yeah. Just take it, instead of doing a difference of means, just take your values and do the ratio.
But what if you can have zeros in your measurement?
Shouldn't be doing a ratio.
Shouldn't be doing a ratio.
How are you going to do a ratio if the value is 0?
Yeah, people do like for RNA-seq. Sometimes people just do +1, do all the values.
Cool. You do +1. Just add, I mean, again, there's nothing here that tells you it's a good or bad statistic. It's just a method for determining if your statistic is different than chance. So if you think that's an accepted statistic, take your 2 values, add 1 to them, and then have that be your formula.
And the other question, very practical question is, let's say that we want to use your beautiful codes, but let's say that like if I have like a very big data set, and so I have to do it from the cluster, like how do can I run that from the cluster?
I don't know. I don't know your cluster. If it runs R, then it seems like it should.
But it's because like I'm just concerned because they're saying because like it works only if you need to. If you do need.
Oh no, you can copy and paste the code. It works just fine. So if I just take all my code, ignoring the dots, the squiggles, I copy it and paste it, it'll work just fine.
So that was not working for us because
I don't know.
we were doing something.
Yeah, you're doing something
I
wrong.
think it's because the interspersed.
You can't copy these.
You have to take it.
That's just for making it look pretty.
That's just for the HTML.
What else? Because we only got 2 minutes. Having a what? Okay.
And we are measuring like response and want to see if the response is good or response. There are 2 ways. I think like first is you just like do the t-test. The other way is like I think it's build the media model, which is like the counting for those whichever treatments versus the
Sure.
and like adding another
random fact as a replicate.
Okay.
See how that's
And that's what? And then what do you get? And then what? What's the question? I get the background.
It's like one way is like saying like is that different from zero? Like you would have to consider the effect of the value.
That sounds pretty detailed. Why don't we talk about it afterwards?
Okay, yeah.
Did you have a question?
Can you
Depends how you want to control for it. Sure. How you can control for it. Well, what do you use? R, MATLAB, Python, SAS, SPSS, MATLAB, SPSS. Yeah, I don't know. I don't think we use that anymore. Which is cool. Yes, you can code it in. I don't know what method they use to control for a variable. Usually, like, I would take the variable. We had to do this. We had a paper on anorexia, and one of the reviewers complained that while we found a difference in white matter, it might be explained by their body weight. And so we took body weight, that was what we wanted to control for. And what literally is going on under the hood is they'll take body weight and you'll do a linear regression of body weight onto white matter, let's say. And so it's, you try and predict, and whatever it predicts, you subtract out. That's what a control is. Basically, cool, whatever predictive power body weight it has on what I care about, I'm going to take it, subtract it out, and then I go back to what I was doing before. So I guess I've never done it in a package. I would just do it manually. But maybe that's less pretty. Yeah, sure. Because then any impact of body weight on brain mass has been regressed out, and whatever else is independent of that. Yeah, sure. All right, thanks everybody. You're gonna get a survey. Will you please answer it? Great, thanks. Sure. Stop share.